Good evening, YouTubers. This is the second part of the video about process control in where we are using a PI controller, proportional integral controller. The system or the PNID that we are talking about is like a vessel shown here with some agitation or so, in where there's a flow of material getting in and the level of this tank will stay the way it is, so there's no mass. The mass inside this vessel will not change, and therefore the exit here will be the same as the inlet. So it's M1 here will be like a M2, but it's equal to M1. So now for this system we have a resistance here. It's a heating element, and basically that heating element is controlled by either by voltage, could be a VFD, a variable voltage regulator, or a variable frequency drive, whatever, by whatever means that you can control from the maximum energy that this element will emit, to zero when you shut it off. Now that's come from this controller. So I measure the temperature. Based on that temperature, I compare that with the set point and then calculate what will be the COR that will control the flow of heat into this vessel. The model for this was discussed in part 1. I'm only talking about here how can we do this within Excel so that we can entertain many variations in terms of parameters and so forth. And talking about parameters, for example, the best thing that you can do with Excel is to list the parameters that you're going to be impacting. Like, for example, what are the watts, that the maximum watt that this heating element will produce. We're talking about 5 kilowatts here, shown here. What is the COR bias, and where are we going to be leaving this, or if this system will be starting, so that you are doing process control based on a known value of steady state. And so with that COR bias, you set what is the steady state value. So now with this value, you can calculate QR. Basically, that's what the way it is here. I'm showing you the equations as I move around, and that's QR. How about here? The maximum flow is based on 2 gallons per minute that can go through here. At that rate of 2 gallons per minute, that will end up being about 1.26 kilograms per second. We're gonna adjust this valve to 30%, and that will give you this flow. So those are the calculation there. Now the volume for this vessel, or the amount of liquid that is here, is about 30 gallons. That will provide a mass of 113.55 kilograms based on the fact that the density of water is 1 kilograms per liter. Now the delta T on this analysis is going to be 10 seconds. That's plenty of time to do this. It's fast enough, to carry on the integration process of the differential equation that we developed in part 1. And tau I is going to be set at 500. This value, I wanted to show you what will happen when you start to mess around with this value, with the 500. What things can, that will not happen when you have a proportional controller, but it does happen here when you have a proportional integral controller. Now KC is about 10. T1 is the temperature, the temperature here, the inlet temperature. It's about 25. The set point we set at 50, and this 50 comes from the fact that we did some calculation of the steady state equation for this system. At steady state, it will produce, like for example, at maximum at 5 kilowatts rate of heat in, it will produce a temperature of about 56 coming out of here, versus when there's no heat, obviously the temperature in, it will be the temperature out if this is off. That would be, since this is 25, then the temperature at T2 is going to be 25 as shown here. I put an equation there so you see, but it's obviously, if QR in that case will be 0. On the other hand, in this case, QR is C4, and C4 is right here. That's the maximum. That's the maximum. So I hit that, and that's why you see maximum there. And this is just a steady state value where we're gonna start the controlling process. Where are we gonna start? Well, we are starting from the steady state value for a well-known steady state value that is about 40.82, and that comes from here based on the fact that you establish a bias. All right, so with that said, then the next thing is to establish the control table. We did this and it's shown here at part 1. Obviously, I only carry out 2 lines of the control table, but here in Excel I did many lines within a few seconds. So the idea is this: we do what we did in part 1, but at time 0, then the most important is where you're starting. Well, we're starting at steady state value of 40.82, but we want a set point as shown here of 50. So we want more heat to get in, so eventually the temperature coming out of here, T2, will reach the 50 degrees. Now, when you establish that, you see that's coming from this table above here from the set point. Then the next thing is, what's the error? The error is basically the set point 50 minus E22, which is this one here. Enter. What is the area of the segment? Remember, we are using a PI. The area of the segment, or the integral of that particular segment, since there the delta t is 0, you have an advance in time, that will be 0. The sum obviously is 0. So these 2 terms are used for the I part of the PI. Now, the CO calculated, I have the whole formula here. Let me put it down. So it's going to be the bias 50 plus C14, which is the KC value, times C22. Now C22 is the error here, plus C14 KC over C13, which is tau I, this one here, tau I times the sum. At this point, the sum, which is E22, in this, it's behind this, is 0. So the integral part is still not active yet. So that gives 141.78. Now, if I double click on that, it means that this equation will take care of correcting that number that is above 100, and it will set it to 100, which is kind of nice. So I'm gonna set yes, and that's what you see here, the 100. So, and this will impact this one, as you can see, and so $4 is QR maximum, but that multiplied by the corrected value on G22, this one divided by 100, that will give me will provide the actual QR or heat. So that will be supplied to the vessel, which in this case is going to be maximum, because that's the maximum value of this resistant element here. Now, so we complete the first line, that's it. Now let's go to the second line. For the second line, we increase the time to 10 seconds by 10 seconds. So that's, you see here the number here before, B22 plus $12. $12, that's delta time, or delta t, which is in this case 10 seconds. So that would be 10 and so forth. How about the error? Well, the error is, again, we need to calculate this number first. So before getting into the error, let me discuss this number. This is the integral of using the Euler method for the differential equation that describe this system, how this system is going to be heated up. Now, the Euler equation of that differential equation will end up like this. So it's going to be the value, this value here, plus the delta t times $9. If you check that out, again, this is coming from the model, from the part 1 of this video, part 1. So $9 is m dot, so you end up here with m dot over the total mass of the vessel, $11, which is this one here, 113.55, times T1, and T1 in this case is 25, minus I22, which is this temperature here, back again, and plus, careful here, H22, that's the actual QR, which is coming from here, divided by $11. That's again this here, divided by CP value, which is 4.18. That's pretty much done. And we set enter, so the temperature increased a little bit. Now check this line and check this line. This was done by hand, so for they're pretty much identical. 41, this is 141.78, 105. Next line is 10. I got 9.12 here, I got 9.13. That's okay. Now the next thing is, here is the first calculation of the area for the segment that can be done, right? You check is the average of the height, so C13, this one here, and plus C22, this is here, you see C22 and C13, the one that is behind, the average of that height multiplied by $12, but $12 is the distance, or the delta T time. So that provide the area. Now for the sum, let's go back a little bit here. As you can see, I anchor the first value, and whatever when you drag this, it will add up whatever is on this column. So that's how it works. So as you can see, it's showing 91.51, which is this value. And since now we have the contribution for the integral part of the PI controller, so we can go here and do the calculation, which is the same as above, but now the sum, which is E23, is not 0. So there's going to be a contribution coming from the PI. Small, but there's going to be one, and that's the point. So here we are. 141.78 is changed to 143.00. Again, it's above 100, so it's corrected to 100 as per that formula there. And then QR max is right here. And finally, we finished, because we already calculated this. Remember, you have to calculate, for example, for the next line, let's see, 0, 10, 20. The first thing you do is get this. And when you get this, then you get all the other part within that. The idea is that basically, I would say the most important part is to ensure that before you drag, you anchor what needs to be anchored. For example, anything from 19 and above up to 4, if you use any of these part of the table, need to be anchored. So that's the point. And for example, delta T, this is the error. So the error is the set point that need to be anchored, because it's right here. So that's C16 minus E23, which is this value here. Oh well, that's basically it. Now, there's nothing more into this table that I can add. The fact is that you just drag it, and that's it. You keep, I drag it, and you can see that the temperature is going up. This is the temperature, and this is the time. It's going up at 150, but as you can see, it stayed the 5 kilowatt of energy being supplied to the tank. Keep adding, keep going, keep going. Finally, it hit the 50, but it don't stop. It don't stop because probably one of the things that happen with PI controller is that they saturate, and it take a while now to come back, and that might be a problem. And that's why besides the PI, there is a second PI type of controller. It's a PI with anti-wind up. It's called with anti-wind up. So you don't allow, when you get to the 100%, you don't allow this number, the sum, to increase to a crazy number, because as you can see, it's huge, and that is causing that beyond the 50 degrees here, you are still allowing this QR to be that big, and that will overshoot. So the temperature will go up to 51, 1 degree above, 2 now. So, and it's not reacting. You can see the number is dropping, but it's not dropping fast enough, and because it's saturated. Eventually it hit the 54, well no, actually 53. That seems to be the highest number somewhere. Now it's dropping. As you can see, it's getting smaller. It's dropping. Now it went down. So it's sort of like oscillating. That's what's happening with those values that I have right now of tau I around 500 and Kc about 10 is causing some oscillation, and eventually it will hit back to 50.12. It's not yet at 50, so if I keep dragging these, I will do so. Only drag them just to show you. Eventually it's gonna start to drop. Let's see where we are here. 50.12, still not here yet. It's not there yet. See, it keeps oscillating. Now it's 49.98, and eventually it will get there, but it's gonna take a while. Now, this is the story. Here we have the PV value of temperature. I started around 40, 42 here, 40.82, and it went up to the 53 or so, and then it dropped and then went up until eventually it's gonna get to the 50, no question asked. This is the COR, or the signal from the TIC, so it stayed at 100 even when this was, you know, way above the 50 mark here. But then eventually it realized that it was way too high, and it dropped it to eventually start to get to a kind of a steady state value, and it will stay there until this hit the 50. Now, very important, remember, this is what we call it the system that will auto regulate. And let's say that tau I, instead of being 500, is a huge number. When you make that number big, since it's in the denominator for the controller, that will basically shut off the integral part. So one way to shut off the integral part is to make this number big, like 1 to e to the 6. That's huge. And this is what's going to happen. As you can see, with only Kc value as shown here of 10, you don't get to the 50. You stay around 48. So a P controller on this system will not be that great, because you would not reach the temperature you want. So you want the PI. So you want the action of the integral part to ensure that you reach the 50 mark. You can try to make Kc big, and that might work, but there's a problem with that. Let's say that you start to make Kc, this value here, big. How big? I don't know. Maybe 5,000 or 10,000. Let's say 5,000. Let's see what's happening. 5,000. That's a problem. See, you are reaching what you want, the 50 degrees, but there's a problem with the controller. The controller is going definitely on and off, on and off, on and off. It's shutting, you know, and that's what you see here. Maybe this was not designed to turn on, turn off that fast, and it will damage the equipment. If it's the electrical motor, definitely will kill the motor. You can't do that with a motor. And not good either. You are trying to control a VFD going up and down, you know, that's not good either. So again, this happened because I make Kc huge, and I eliminate pretty much the integral part, and it will cause oscillation that will probably damage that equipment. Now, going back, let's fix this mess. So going back, let's get this to a small value of 10 again. And now let's get this value to a more realistic number. Let's say that this value is 10,000. Still, 10,000 is, big. That probably what you're saying is that don't take too serious the integral part. That's when you put that number that big. Now, as you see, I'm almost hitting the 50, but it's not gonna work. It's staying there, and it probably will hit the 50, but it will take for a while. And on the other hand, the oscillation on the controller was very small. From 100, it dropped to a little bit less than 80 and stayed pretty much there. Now, how about if I drop, let me get this tau I in the, let me change the format, because the format, I don't like it. Let's put numbers and let's say okay. Now, instead of 10,000, how about if I drop it to 5,000? Definitely 5,000 looks a lot better. I believe that probably it hit what it need, the 50. Let's see. Yeah, it's getting there. You see, it's increasing somehow with a, like it's dampened, you know. It's not oscillating, so it's 49.9. If I keep, you know, uh, it might work. But let's go back here and let's get this number from 5,000. Let's drop it to 1,000. Changing the tau y is a weight now. I got on is overshooting, and that you don't want that, because that overshooting will cause to drop down and then go up, and definitely I don't want that. So there's, for example, if I keep dropping this from the 1,000, you saw what I did with the 500, a little bit more oscillation. How about if I keep dropping the in this case tau y, the integral part for the, or the time constant for the integral part, from 500, let's say 100. More oscillation, and the bad thing is that from 100 it really dropped to 0, and then it took a while to go back and get back into 100, and then it dropped back, but I still see a lot of oscillation, and that's not good. But let's keep doing this. 100, how about 50? It's gonna establish oscillation, and you are not gonna get the set point that you want. It's gonna oscillate a lot, and again, you can resolve all that. Let's get one smaller, 25. See, no, not good, not good at all. So let's go back. So the value, the optimum value might be around 1,000 somehow. Let's see, 1,000. But 1,000, it go up. I don't like this. Maybe that overshooting is not good. You don't want overshooting, particularly if you are working in a pharmaceutical and the temperature has to be limited to 50. You don't want this to happen. So you want to damp that PV to be under. So underneath, it will do this until it hit the 50. So that's really what you want. So to do that, then this value might be like 2,000. Looking better, still a little bit above the 50 and coming down. So how about 3,000? Getting a lot better. 3,000. I don't think that there was any overshooting. Let's take a look here at the table. Yeah, a little bit. The highest was about 50.33, 34, and then coming down. I would say perfect. That's basically it. So a combination of tau I of 3010 and a combination of tau I of 3000 and a Kc of 10 provide a pretty good and a decent behavior for the PV to reach the desired temperature. Again, you can increase Kc and tailor tau I to behave, accordingly. Again, there's a technique to do optimum, to get the optimum value for tau E and Kc, and that's what the kind of a third video, because that's open loop. If you do an analysis of open loop of the behavior of this vessel in open loop, you might come out with the proper Kc and tau I value as required for this system. When you have that, then you can keep tuning. Right now, what I did, I got this number from the blue, or from experience, and try to tailor them to behave nicely so that I get a good process control curve as shown here, and that the behavior of the control part is not oscillating either. So because you don't want this to oscillate and you don't want this to oscillate either. A little bit of oscillation is okay, but too much is not good. Again, that's basically it. I don't think that I have to add anything more into this video, because the idea was to show you the Excel table that you can do PI control, and that the area of the segment and these two parts come from the I part of the PI controller. And anything else here? Nope. look good. Everything else pretty much the same as we did with the proportional controller. As always, thank you for watching. See you on the third part, which is for open loop. Have a great day. Bye.